quick recap on exponential and logarithm equations, because as we move forward, we're going to need to add those to our list of potential equations. So remembering that an exponential equation is one where you have some sort of a base raised to an exponent. We'll look at the graphs of exponential equations in a minute at the end of this, but that's an exponential equation, where a logarithm equation takes those same letters and just rearranges them, because the logarithm equation is the inverse of an exponential. So it's the way to undo an exponential. So if you need to solve for x, you can take the log of both sides. There's a couple of different properties. The properties don't really matter too much with exponential ones, but what we do is we do some different things with logarithm equations, like the different properties exist where if you have log base b of a plus log base b of y, what we can do with that is we can combine those. Let me just use a different letter. Let me do a couple different letters. Let me make this m and this n. We can multiply those when it looks like that within a log. If we have log base b of m minus log base b of n, what we'll get on that is we'll get log base b of m divided by n. So we can divide like that. And then maybe the one that we use most often in calculus is if we have log base b of m to the n power, what we can do with that is we can bring that power out in front. And that's probably the most powerful one. That's the one we'll end up using a lot in calculus. If you just see log of x without a base written, that's log base 10. Oftentimes we just won't write a base if there's no base, or if there's no base, it's just assumed that it's log base 10. The other thing is that if you see this idea of the natural log, that's log base e. So, and the natural log is used a lot in exponentials because of the exponential power. So, for example, if y equals the natural y, let's say y equals e to the x, then x is equal to the natural log of y. So these two kind of go together. But they would follow the same rule as these two. And here are all the properties. We're going to use those in some just examples that I'll do. Some I'll simplify, some I just will leave and not simplify using a calculator, because that's just plugging it in. I think you can find if you look on your calculator, you can find the log key right next to the 1 key. You can find the log and the inverse, and you can see how they're just the control button away from creating the inverse, and that's really the way all calculators work. Is they have 1 key, and then the inverse is the second or control button. So that's how those functions are really closely related. So take something like this. We don't know what maybe this looks like, because we don't have our calculator actually could compute this. If you type in log, I think you have the opportunity to change the base on these calculators. But Another way of logically thinking about this is if I write this equation in an exponential form, then 81 would have to equal 3 to some power. And now I just got to figure out what that power is. I mean, you know, 3 to the first is 3. 3 to the second is 9. 3 to the third is 27. 3 to the fourth is 81. So x has to be 4 in that case. I should write that in normal order. So there, x is equal to 4. But if I think about it, that log equation in an exponential way, then I might be able to come up with an answer. I can do the same kind of thing with something like this problem right here. Take this problem right here, and if we change this to an exponential, this would be 4x is equal to 3x to the third power. Well, that means 4x is equal to 27x cubed. And now we could solve this, because what we could do with this, you don't need to solve it, I guess. But we could solve it. This is the exponential. This one says you just need to write it. But let's say you had to solve it. Couldn't we just write this and then factor out an x? We'd have 27x squared minus 4, and then we could solve that. You know, we could solve that into x must equal 0. Well, we'll talk about why that doesn't work, because in a little bit we'll talk about why that doesn't work. But you could go through and solve that. Okay. Write this log equation as an exponential. You don't need to solve this one. Remembering this is the natural log, right? So remembering that the natural log is the same thing as log base e. So remembering that's the little trick that we have this power e. So e to the 3x must equal 3x plus 2. Now that one would be really pretty difficult to solve, actually. You might need a calculator, but they're not asking to solve it on the assignment. They're just saying write it. When we start using some of the properties, take a look at something like this. Well, if we kind of think about what this could be, we could start by saying, well, isn't this log base 4 of x squared minus 2 times 3x, or divided by 3x plus 2, right? Using the condensing of the bases, we would have that division there. That's that second property I wrote down. Well, once we have this, then we know that x squared minus 1 divided by 3x plus 2 has to equal 4 to the 0 power. Well, 4 to the 0 power is just 1, right? I mean, so you should know that 4 to anything to the 0 power is just 1. And then we could take this equation. We could say, well, that means x squared minus 1 has to equal 3x plus 2. And solving this, x squared minus 3x minus 3 equals 0. And if we factor this into x, how does that factor? Not sure how that's going to factor. Oh, I wrote something wrong on there. Sorry. You maybe caught it, but this should be a 2, and that will help me. This should be a 2 here. Should be a 2 here. And we should have minus 4 here. So we can factor this into x minus 4 times x plus 1 equals 0. So that means x is equal to 4 or x is equal to negative 1. Well, if you plug it in, one of the things that you should know is you can't take the log of a negative value. So that negative 1 is going to be a problem. So actually, this is the only answer because this one is what we might call an extraneous solution. We'll talk about that when we look at the graph, and you'll see, oh, that's why that negative 1 didn't work. So you can go back to that. Last one here, solve this exponential, or solve this one, and find the exact value, which means don't use a calculator. That's all that really means. That's what that means. Don't use a calculator. So if I were doing this, I'd say, okay, well, let's just clean this up a little bit. 2 natural log 7x minus 8 is equal to, subtract 10, negative 4. So the natural log of 7x minus 8 is equal to negative 2 if I divide by 2. And now we could say that e to the negative 2 is equal to 7x minus 8. Because remember, the natural log is base e. So if I just wanted to not simplify, which I don't really care if you simplify, e to the negative 2 plus 8 divided by 7 is equal to x. Now I just added 8 divided by 7, and that would be a fine answer. I know you can simplify that, but I'm not going to. That's an answer. You could type that into your calculator, and your calculator will give you a numerical value that's equivalent to that. It would be a decimal because e is an irrational number, so it would be a decimal, and that's okay. And if you're ever going to report things on an AP exam, report to 3 decimal places. So last thing are graphs of exponential and log functions. If we graph exponential functions, any exponential function, so y equals a to the x power, any exponential function is going to look like this. It has some pretty unique features. It has this feature right here that it always is going through when x equals 0, y is equal to 1. That's because anything to the 0 power is 1. It also has a feature over here that if you go over to 1, this point is 1 comma a. Okay, so that feature. You could do exponential decay and it just flips it over. Now, if you look at an equation where you have a log equation, because they're inverses, they view like inverses. So you have y equals log base b of x, something like that. If I were to graph that one looks like this. Has those same points, but they're reversed because they're inverses. So this is 1, 0. And there's a point up here that's a, or in this case, b. Comma 1. And let me just, to be consistent, let me put the same letter in here for you. So you can see that those are inverses. A couple things that are true about these equations. They're both monotonic, which means they are always increasing. Okay, that's what monotonic means. They're always increasing. Over here, there's a horizontal asymptote that is y equals 0. Over here, there's a vertical asymptote of x equals 0. Go a little bit further. The domain on this one is from 0 to infinity, not including either one of those. And the domain over here sorry, wait a minute. Domain on this first one is negative infinity to infinity. And the domain over here is from 0 to infinity. And then the range on this one is from 0 to infinity. And the range on this one is negative infinity to infinity. I mean, they're truly inverses. So what's true for one is the opposite is true for the other. So hopefully this will help you do the assignment today. If you have questions, always ask.